Hello everyone, my name is Ahmed Ned, and today I'm going to do our work presentation, Player Identification in Different Sports. And this work is done in cooperation with Said Hamid from Cairo University. Okay, so first of all, this is a summary of the presentation. To begin, I will introduce the problem statement and talk about the motivation of player identification. After that, I will talk about the approaches of player identification in the introduced sports jersey number dataset. Then I will explain the pipeline for player identification through the jersey number that we proposed and the experimental results on the introduced dataset. Finally, I will conclude our work and show the potential research direction. Okay, so what is the problem statement of this work? The problem statement also identifies the player in unconstrained sports venue across both matches and sports. So, what are the motivation of doing player identification? The motivation for player identification are its usage in several applications, such as personalized radio summary, player statistics, for example, player's distance covered, number of shots, number of passes, etc. And based on player statistics, we can evaluate weakness and the strengths of the player and the team. Player identification also can be used in tactical analysis and player scouting. The features that are employed for player identifications are faces and jersey numbers. But approaches that rely on face recognition for identification operates in close-up shots, where the player face appears clearly and became invisible for overview shots due to low resolution of a sports player. The other visual cue is the jersey number. The jersey number is a physical cue that is common and generic across the sports. The approaches based on jersey number are promising due to jersey numbers occupy large part of player back and the rising of LHD sports fit. The challenges of jersey number recognition are not limited to the variations of player pose and motion player and variations of camera viewpoint, but also include the distractions inside and surrounding playgrounds such as clocks, commercial logos, and banners. Since there is no publicly available datasets for jersey numbers, we introduced the sports jersey number dataset. Sports jersey number dataset has three different subsets, as shown in the figure on the right. In the first row, should represent detected players from the first basketball subset, and the second row represent the detected players from the second basketball subset, and the third row represent the sample images of detected players from the ice hockey subset. The sports jersey number dataset represents detected players in various situations, such as the subfigure A and F, G, and K represent player images in normal situations, but the subfigure P and J, P, J, and I represent player images in variations of player pose, and subfigure C, H, and M represent player images with non-back jersey numbers, and so on. The statistics of the dataset are listed in the table as follows. The first subset contains 1,872 player images that are extracted from set of video clips, and and the player images are annotated with the bounding box around the jersey number regions and its class. And in the second subset, the number of player images is 850 and 51 player images that are extracted from 1-minute video clips sampled at 5 frames per second, but in different basketball arena. The third subset contains number of player images 1,317 player images, and those images are annotated with jersey numbers and extracted from 1-minute video clips sampled at 5 frames per second. So the overview of the proposed method is illustrated in the structure of the proposed framework figure. The proposed framework has 3 main steps: sports player detection, text or number, jersey number detection, and jersey number recognition. In the first step, YOLO version full object detector is utilized to detect the sports player on the court. Then the text detector is used to locate jersey number regions on each player in the second step. Finally, the detected candidate regions are recognized using the text recognition model. We treated the jersey number recognition as syntax trading problem. So we provide more details about jersey number detection and recognition. Motivated by the character region awareness or text detection methods, state-of-the-art performance, and the generalization ability, we adapted to detect number regions on player t-shirt, whether from back or front. To account for jersey number challenges, such as variations of player pose and variations of camera viewpoints and the jersey number fonts, we fine-tuned a craft model on a first subset of the sport jersey number dataset. Also, the used image augmentation techniques are scaling rotations, color manipulations, and Gaussian play, as illustrated in the figure on the right. Subfigure A represent original player images, and subfigure B represent player images after applying scaling. C represent the player after applying rotations, and subfigure D represent the player images after applying communications, and finally the E represent player images after applying the image augmentation Gaussian clip. In the jersey number recognition step, we use the image-based sequence recognition to recognize jersey number as a whole. For 2 reasons. The first reason is to overcome the difficulty of dividing a 2-digit jersey number, and this is because of non-upfront reviews and numbers destruction. The second reason is to address the challenges of not having a dataset of all possible jersey numbers. We employed, for this purpose, 4-stage attention-based text recognition framework introduced in What is Wrong with Syntax Recognition Model Comparisons, Datasets, and Model Analysis paper. The framework is composed of 4 stages as follows: transformations, feature extraction, sequence modeling, and predictions stage. In this slide, we present the experimental results for number of detections across different sports, ice hockey, and the basketball sports. Subfigure A and B represent the number detection using a pre-trained craft model on an ice hockey and a basketball subset respectively. Also, the subfigure C and D represent the number detection using a fine-tuned craft model on the same images from the ice, hockey, and the basketball subset respectively. From this figure, we notice that the fine-tuned craft model can detect jersey numbers in different and complex situations compared to the pre-trained craft model. And then we conduct the comparison of number level accuracy among approaches. Among the following approaches: Gerg et al., A et al., and baseline and our framework. The baseline framework is composed of pre-trained general craft detector, followed by attention-based text recognition model. From this table, we can notice the baseline framework outperforms both related work, Gerg et al. And Lay et al. In ice hockey subset and second basketball subset. And the introduced framework accomplishes even better performance on all subsets of the sports jersey number dataset due to its robustness to variations of player pose and variations of camera view. In the application study, we investigate the following: an input player insights and a method of prediction module of the 4-stage text recognition. In the application study related to the input player insight, we conducted experiment to select a suitable input player image size for number of detections where it may be different for each sport. So the upper table shows the proposed accuracy on a sports jersey number dataset based on the longest input image size. From this table, we can notice that the longest image size, 192, achieved better performance on basketball sport, where in ice hockey sport, the better performance is gained by the longest image size, 106. For the second ablation study related to a method of prediction module of the 4-stage text recognition, we need to assess the performance of our framework by replacing attentions to the web, the CTC connection symbol specifier. As shown from the lower table, we can notice the attention-based recognizer outperformed the CTC-based recognizer on all subsets of the sports jersey number datasets. The failure cases of our framework return for 3 reasons. The first reason is the distractions in the playground, such as drugs and banners, as shown in the subfigure A. These distractions can be recognized as a number. As shown in the subfigure A, the leftmost player image in the subfigure A can be recognized with the jersey number 23. And this is distractions, not a number printed on the player's shirt. The second reason for failure cases is the misdetection of player jersey number. The misdetection of player jersey numbers occurs in players' tilting images and the small number of player images as shown in the subfigure C. And the reason for occurrence in player tilting images is the number in those images is 1-digit number with a font that makes the digits appear discontinuous drop. And the reasons for misdetections in small number player images, not the small size of the number regions, but also the image layer. The third reason for failure cases is recognition error. The recognition errors results from recognizing a number either as a different number or a sequence of characters, as shown in the subfigure B. The leftmost image in the subfigure B can be recognized as number on the player's chart can be recognized as a 7 instead of 1, and the rightmost image in the subfigure B with the just number 10 can be recognized as 2. Finally, through this work, we presented a compound deep neural network for force-reverse number detection and recognition, and the experimental results demonstrate the efficiency of our method in field of computing them on the introduced force-reverse number dataset that contains player images from different arrays and squares. Also, the potential future direction is to reduce failure cases through reducing number misdetection and recognition errors.